let's review our concept of a random variable. So a random variable is a function from the sample space, big omega, to the set of real numbers. And to define it, we need to specify the triple, omega, and a sigma algebra defined on omega, and then a probability measure. The random variable is not an arbitrary function. It must be F measurable. And so it means that the pre-image of any Borel set should be part of your sigma algebra. This is guaranteed if it happens that your sigma algebra is a power set, but like especially when big omega is uncountably infinite, we are basically forced for mathematical consistency to have our sigma algebra as a proper subset of basically the power set. And hence, not every subset of big omega will be in the sigma algebra. In that case, we will need to check that, again, the pre-image of any Borel set should be in this selection of subsets of big omega in the sigma algebra. Otherwise, we don't have a random variable. We have a function defined from big omega to the set of real numbers, but it is not a random variable. Now, there is a very useful theorem, that we are using here, which is you do not really need to investigate every Borel set. What you need to investigate are basically those specific Borel sets in the form of the infinite intervals from minus infinity to x, small x included, where small x is basically a real number. So random variables, they come in a number of basically types, and the first type is the discrete random variable, which takes finite or countably infinite values with probability 1, almost surely. Okay, the image of x itself may be actually uncountable, and we have seen an example in the previous lecture. Okay, but by the end of the day, when you transfer the probability measure from the sample space to the random variable, to the set R and the Borel sigma algebra and Px, then when you do this transfer, then the probability that x is in a finite or countably infinite set is equal to 1. So in that case, we say that our random variable x is a discrete random variable. As a digression, I think I said this already, but not bad to say it again, that in many applications, we do not really, think thoroughly about big omega and the sigma algebra, and then define a probability measure, and then transfer the probability measure to the random variable x. In many cases, we just take this for granted. We start with the set of real numbers and the Borel sigma algebra, and actually we assign the probability measure to the random variable directly. Say, okay, that the random variable x is geometric, is exponential, is Gaussian. Okay, and so that's the reason, maybe in a previous course, and actually in many applications, even if you are doing advanced stuff, you may actually just work with this triple here, and forget about big omega and how actually this guy is obtained. Sometimes it's obtained just by assigning. You just think that in some for example, the distribution of the heights of people, that it is good to basically model this using the Gaussian distribution. Okay, and so what I am saying does not necessarily mean that random variables in practice will always be basically obtained in such a way in which you have big omega, you define a function on big omega, and then you make sure that the function is F measurable, and then you transfer the probability measure and so forth. Okay, so this is not what happens in the, but this this understanding of random variables may be important in some other applications. Looks like if you study things like almost sure conversions of a sequence of random variables and so on. Sometimes it is really important to go back and understand how a random variable is actually defined. So okay. let's go back to the types of random variables. An absolutely continuous random variable is defined in such a way that basically the probability of any Borel set. Okay, so this is the probability basically of the measure of the random variable, the probability law of the random variable. Now, if you put here, I mean, you can feed it any Borel set. And for practical applications, typically the Borel set will be in the form of a finite or an infinite interval. But you know, in theory, you can basically feed it any Borel set of your choice. So this is B, which belongs to the Borel sigma algebra. And basically, a random variable is absolutely continuous if the Borel set that you are talking about is of Lebesgue measure 0. So in one dimensions, this is like saying that the length of the set is equal to 0. Then it must be the case that the probability of this Borel set, you know, is equal to 0. So every Borel sets of Lebesgue measure 0 should basically be assigned a probability to 0. And that's case you say that your random variable is absolutely continuous. And so what are examples of Borel sets that have a Lebesgue measure 0? Singletons, you know, so basically sets that contain just single elements, sets that contain a finite number of elements from the set of real numbers, actually sets that contain a countably infinite basically number of elements. So something like the set of rational numbers, the set of algebraic numbers, the set of computable numbers. These sets are huge, these sets are dense, but still, you know, if you compute their measure, they have a measure 0. Okay, again, because measure 0, this, you know, it's basically a definition. You know, if you can cover a set with, you know, in one dimension with a bunch of intervals, and then you find that the overall length of these intervals can be upper bounded by something that can be made arbitrarily small, then that's it. Then the set is of measure 0. And if the set is of measure 0, then again, and our random variable is absolutely continuous, then the probability assigned should be equal to 0. And there are some uncountable subsets of the real numbers that actually have a measure 0, like the Cantor set. Okay, so all those guys must have a measure 0. For those random variables, what is like, you know, what is like more known about them is basically this idea of the probability density function, a PDF. So those guys, they have a PDF, and the PDF is the Borel sigma algebra just the Borel sigma algebra includes all types of intervals that you think of, includes all their complements, include all their finite or countably infinite unions and intersections, and so on and so forth. It is a sigma algebra. So it has the properties of a sigma algebra, and we are sure that it includes you know, typically you start by saying that we are sure that it includes all open intervals, but then starting from this and applying the properties of a sigma algebra, you can show that it includes all the singletons, and then that it includes all types of intervals, whether they are open and closed, and then you can take these intervals, and again you can do intersections, you can do unions, you can do many things. And so there are so many subsets of big R that are in the Borel sigma algebra. Okay, so they include the intervals, and much more. Okay, including, you know, intervals like this one, you know, the interval that is basically used in the definition of the CDF. So the Borel sigma algebra, again, it is a sigma algebra. Okay, so by definition, if you put something in there, you should put its complement. And if you put some stuff in there, you know, then you should include finite and countably infinite unions and intersections and so forth. Okay, so the Borel sigma algebra, again, it's difficult to think of a subset of R that is not a Borel set. You know, so B is one of those guys. B here, okay, so what is B here? It is a Borel set. So B belongs to the Borel sigma algebra. So B here is one of those guys. Now, for the Borel sets, they are Lebesgue measurable. So borderless sets, you can assign a length to them if we are talking about one dimension. So you can assign a Lebesgue measure or a length to them, and if you assign a length to them, then if it happens that this assigned length is equal to 0, so they are basically of Lebesgue measure 0, then if you want your random variable to be absolutely continuous, then it must be the case that the probability of happening is equal to 0. So for example, what is an example of an absolutely continuous random variable? The Gaussian. Okay, so it means, what I'm saying is that what is the probability that you generate a random number from the Gaussian distribution. Okay, and so this is like done in MATLAB using grand N. What is the probability? What is the probability that you get a rational number? Okay, so what is the probability of getting a rational number? Well, it is 0. It is 0. Now, on a digital computer, so things are complicated, because on a digital computer, we don't really have real numbers. Okay, because real numbers, they need, if you want to express a real number, you need an infinite number of bits. But you always have a finite storage, finite memory, and so on and so forth. Okay, so basically, when we do the generation of random variables on a digital computer, we are not actually doing everything on digital. You can think of it as actually discrete. So this is another story. Basically, how do we generate samples from a given distribution? Again, we will be limited by how computers actually work. Okay, but in theory, if you are able, to choose, if magically you are able to choose a random generated according to the Gaussian distribution, and then you ask yourself, what is the probability that this number is a rational number? Then the probability is exactly equal to 0. And this applies not just to the Gaussian distribution, but to all absolutely continuous distributions, like uniform, like exponential, like gamma, like chi-squared, non-central chi-squared, and so forth. Those guys, they have a PDF. The PDF is non-negative. It's a non-negative function, but it is not a probability. So I gave an example earlier that basically it can be a function that is unbounded. Definitely, it can go above 1. But the idea is that this PDF can be used like to compute probabilities. Okay, so it itself is not a probability, but for example, if you want to find the probability that that the random variable is less than or equal to some small z, which is the definition of the CDF, then you take this PDF and you integrate it from -infinity to z. Okay, so this will give you the probability that big X is less than or equal to some real number small z. Okay, now for absolutely continuous random variables, the CDF is a continuous function. It does not have jumps. No jumps in the CDF. Okay, so for discrete random variables, if you remember, so if you have a random variable Bernoulli B, so this is a random variable that is basically equal to 1 with the probability P, and is equal to 0 with probability 1 minus P. Let's recall what is the CDF of this guy. Okay, so here is what is the probability that this thing is less than or equal to 0? Sorry, what is the probability that let's start first with the negative case. What is the probability that this big X is less than some negative number? It is 0, because basically X is 0 or 1. It's non-negative. Okay, so all the way up to 0, the probability, the CDF will be equal to 0. Okay, so this is the fx of x, which is the probability of that big X is less than or equal to small x. So if we choose for small x a negative number, then this random variable is non-negative, and so basically the probability that it is less than or equal to some negative number is exactly equal to 0. Now, what if small x is exactly equal to 0? So we're asking, what is the probability that big X is 0 or less? Well, it is equal to 0 with probability 1 minus b. So what will happen in the CDF is that there will be a jump with 1 minus b, because the probability that big X is less than or equal to 0 is, in our case here, it will be the probability that X is equal to 0, because X is not negative, but it can be equal to 0, and this has a probability 1 minus b. So your CDF here must be equal to 1 minus b, and there is a jump, because if you choose a small x to be any negative number, the probability is 0. Once small x is exactly equal to 0, then the probability that big X is less than or equal to 0 is the probability in our case that big X is 0, okay, because X cannot be negative. And by our definition of a Bernoulli random variable, this probability is 1 minus b. And so this will basically be the CDF at 0. Now, what if a small x is a number between 0 and 1, strictly less than 1? So what is the probability that this random variable is less than or equal to 1/2 or 3/4 or something like this? Well, it is exactly equal, basically to the probability that big X is 0. Okay, and so it will remain constant, and this will remain up to 1. And then if you ask yourself, what is the probability that big X is less than or equal to 1? Well, this is probability 1, right? Because big X is always less than or equal to 1. So there will be another jump, and you jump to the level 1. And this other jump here will be with probability P. Okay, so this is the CDF. This is the CDF of a typical discrete random variable, the Bernoulli one, which is very famous and very useful. And as you can see, there are jumps. There are jumps at basically the values, at the values of X. So if X can be equal to 0 or 1, there you expect there will be a jump at 0, and there will be a jump at, unless you do, you choose an extreme case in which B is 0 or B is 1. In that case, actually, X will be a degenerate random variable that is equal to 0 or 1 almost surely. But, if we take B to be living strictly between 0 and 1, this is what you expect to see for the CDF. So it has jumps. Now, for absolutely continuous random variables, no jumps. No jumps because the probability of singletons is equal to 0, right? So, let's see why is this the case. So for absolutely continuous random variable, so absolutely continuous, then what is the probability that big X is equal to small x? What is it? It is equal to 0, right? By definition. Because basically singletons are sets of Lebesgue measure 0. So the probability, if you have an absolutely continuous random variable, the probability that it takes a specific value is equal to 0. And so in that case, the probability of X less than or equal to X is equal to the probability that X less than X, strictly less than X, plus the probability X equal to X, right? But for absolutely continuous random variables, this is 0. And so these two quantities are the same. The probability that X is less than X, small x, is exactly equal to the probability that big X is less than or equal to small x. Again, because the probability that big X is equal to small x, which is just a single real number, is 0 by definition. Singleton subsets of R all have a Lebesgue measure 0. Okay, and so in that case, we don't have jumps. Okay, we get jumps if these two guys are different from one another, because this guy is strictly positive, and this is what we see in something like the Bernoulli or generally discrete random variables. For absolutely continuous random variables, there will be no jumps in the CDF. Okay, so here is basically one example of an absolutely continuous random variable. So suppose that big omega is the closed interval 0, 1. And basically the sigma algebra defined is the sigma algebra on 0, 1. And remember, basically the sigma algebra on 0, 1 is simply the sigma algebra defined on the set of real numbers intersected with basically the closed interval 0, 1. So there is a theorem called the trace, or it's a result, say it's a result called the trace sigma algebra, which means that basically if you take all, it's general, but its application here will be that if you take the Borel sets on R and intersect them with 0, 1, you will get basically Borel sets, and you will get a proper sigma algebra on the closed interval 0, 1. And let's assume that our probability measure defined on big omega and so on this measurable space, it is the uniform probability measure. Let's assume that we do this map, okay, that if x of omega is equal to x of omega is equal to omega. And this is valid, by the way. So in other words, that you can do the mapping, of your random variable, which like you assign, suppose that your big omega consists of real numbers, right? So remember what is a random variable? It's mainly a function between big omega and r. So a big omega itself, its elements are real numbers. Okay, so I mean something like this makes sense. I mean, so you can say that x of small omega is small omega. You take each real number in the closed interval 0, 1 and assign it to itself. Okay, as a function. And of course, I mean, who says that this function actually is f measurable? Okay, it is. Okay, we don't want like to waste time on this. It is. So, but but this is actually the correct way of thinking about. So you define a function, and then it's not the end of the story, because you need to check that actually this function is f measurable. So in our case here, you should check that basically under this assignment that the pre-image of every Borel set is part of our sigma algebra. In this case, it is. And basically, this will result in the very famous uniform random variable, which I will say it is uniform 0, 1, uniform distribution from 0 and 1, and the PDF. So the PDF is flat. Okay, so that's uniform. So the PDF is a constant that goes from 0 to 1. Okay, but you can define uniform. So there is a generalization. You can define uniform. Okay, from A to B greater than A, and so this will be from A to B, and this the PDF. So the probability density function will be basically 1 over B minus A. So uniform PDF is a constant PDF. It is the PDF itself is not necessarily continuous, and as you can see, there is a jump at A and jump. So this is PDF. I'm not talking here about the CDF. For the so-called uniform random variables, the PDF is constant. It may have jumps like here, and you can see actually that that the PDF can be greater than 1, right? Because if you choose A, for example, to be equal to 1/2 and B is equal to 1, so this is a random variable that is defined from 1/2 to 1. If you have a uniform random variable, so it must be that the PDF should be 1 over 1 minus 1/2, and this is equal 1 over 1/2, which is 2. Because the PDF, if you integrate it, so if you integrate it and you stop at some small x, it will give you the CDF. If you integrate it from minus infinity to infinity, it must give you 1. And hence, if you want to integrate something, so it is 0 here, it is 0 there. If you want to integrate this thing and you want its integral to be equal to 1, then the area under the curve here should be equal to 1. And if this width is 1/2, then the height must be equal to 2. That's very valid. I mean, it's not a problem because this is a PDF. So again, not the PDF. The PDF may have jumps, okay, and the PDF, because it is not actually a probability, then it may exceed 1. But it's important that of course, it is non-negative. This is non-negotiable, and it's integral from minus infinity to infinity. So the area under the curve, if you want to say, is equal to 1. So this is the PDF of a uniform random variable, now defined from 0 to 1. Okay, and what will be the CDF according to the for continuous random variables? The CDF, you can obtain it from the PDF via an integration. Okay, and so if you integrate this flat line here, which is constant, you will basically get a linear function. Okay, so that's the CDF. Okay, so this is PDF, and it has discontinuities, and this is the CTF. Now it is without discontinuity. So this is a very important to keep in mind. This story I'm telling here, that basically for absolutely continuous random variables, their CDF should be free from discontinuity or jumps. Okay, while for discrete random variables, this is the case. You'll find that there are jumps. Now, once you have the CDF, then you obtain the PDF. Okay, so yes, you can do so via differentiation. At that's the points at which the function is differentiable. So basically, you can obtain the PDF from the CDF via doing differentiation at values where x is differentiable. So this is implicit. So when you write a derivative, so you are assuming that the derivative exists. Okay, so you can in the PDF, you can obtain the PDF using this. I said that the CDF is continuous, but it is not necessarily differentiable. So for example, if we go to the uniform case, what is the derivative at this point? So the conventional derivative is not defined, right? Because the slope from the left is equal to 0. The slope from the right is equal to 1. So basically, this function that we have, it is continuous, but it is not differentiable at these 2 points. Okay, so when I say that the PDF is obtained from the CDF via differentiation, I automatically mean at those points for which the derivative exists, and the derivative exists, it has a certain with the limit, and so in this case here it will be the open interval from 0 to 1, but this function is not differentiable from 0 and 1. Okay, and of course, the PDF and CDF they will come to us, again and again and again. This is just the beginning of the story. Okay. What is the third type of a random variable? This will be basically the singular random variable, and this guy is defined in such a way that the probability of a singleton is equal to 0. Okay. So if you ask yourself what is the probability that this random variable is equal to 7 or 10 or pi or e or square root 2 or any real number of your choice, so long as you are talking about a singleton subset of the set of real numbers, the probability is exactly equal to 0. So here the probability of singleton plural sets is 0. Okay, so what is like this? Absolutely continuous random variables. Absolutely continuous random variables. Their probability at all singleton subsets of R is equal to 0 by definition. However, for single random variables, the full probability measure. Okay, so basically the probability, there exists some set. Okay, I will call it S, that is equal to 1, and this S is a Borel set of Lebesgue measure 0, and that is uncountable. So a singular random variable, it's a random variable at which basically if you compute the probability of a singleton subset of R, it is 0. If there exists some Borel, this Borel set should be uncountable. This Borel set should be uncountable. Also, its Lebesgue measure should be 0. And the probability of this big S is exactly equal to 1. So this is the difference between single random variables and absolutely continuous random variables, right? So if our random variable is absolutely continuous, it means what? If you find a Borel set with Lebesgue measure 0, then the probability should be 0. If we are talking about absolutely continuous random variables. But for singular random variables, there should be some Borel set that is uncountably infinite and that has a measure 0, and the probability of this set is equal to 1. So what is an example of this set? We have the counter set. So this is one example. The counter set is a set that exactly is defined as such. It is an uncountable subset of the set of real numbers. Its cardinality is strictly greater than Elif node. Moreover, its Lebesgue measure is exactly equal to 0. Okay, so this is the singular random variable, and so if you want to define a singular random variable on one dimension, you need to define it on something like the Cantor set or something that is similar to the Cantor set. Okay, and so there are infinite variations of the Cantor set. Okay, so there is actually a distribution, a random variable called the Cantor random variable, or the distribution, and this is its CDF. This is its CDF. Okay, now this CDF, it cannot be drawn by a computer because actually the CDF is very, very complicated. So what you see in front of you is, it's just an approximation. Like the Cantor set itself, right? The Cantor set itself, when you construct it by taking some, by doing some step and repeating it ad infinitum. Basically, for the Cantor random variable, here is how basically its CDF is, or how its probability law is constructed. Let's remind ourselves, what is the Cantor set? You start with 0, 1, right? Then you remove the middle third, okay, from the open interval from 1/3 to 2/3 is removed, and after one step you have this. Then you remove the middle third from each one of those guys. So we have from 0 to 1/9, 2/9 to 1/3, 2/3 to 7/9, 8/9 to 1. You never stop. You never stop. And again, you can show that once you do this procedure, you take it to its end, quote unquote its end, then basically are left with a non-empty set, and this non-empty set actually is uncountable, and its Lebesgue measure is equal to 0. Okay, so basically the probability law of something like a Cantor random variable is defined as such. The probability, all Cantor numbers are between 0 and 1, and so the probability that they are between 0 and 1 is 1. Okay. Now there are no Cantor numbers between 1/3, 1/3, and 1/3 and 2/3, right? Because this is a part that is removed during the construction of the Cantor set. So basically, the probability that x is here or there is equal to 1, and we divide this probability equally. So we say that it is equally likely that you find the Cantor number between 0 and 1/3, or between 2/3 and 1. So the probability of this interval here and that interval here is equal to 1/2. And you keep doing this. So at the third step, there are parts that are removed. So we are sure that there are no Cantor numbers that are there. The probability of getting something there is 0. And then you are left with 4 segments. You assign a probability of 1/4 to each one of those guys. Okay? And so on and so forth. And then you get this basically strange CDF. So for example, this one here, the probability that x is between 0 and 9. So this is actually the CDF of 1/9. And if you go here, you will find that basically here is 1/9, and this is 1/4. Okay, so this is the CDF. Does the CDF have jumps like what we see for discrete random variables? What do you think? Does the CDF have jumps? Yes? No? No opinion? No. The issue is that singular random variables, they are defined so that the probability of singleton subsets of big R are 0. Okay, so remember, it's not, we have this one, we also have this one. Okay, so a singular random variable, it's 2 things. That basically the probability of a singleton is 0, and then there exists, this foreign set of Lebesgue measures U that is uncountable, in which the probability is equal to 1. But don't forget this one. So it means what? Remember, when do we have jumps in the CDF? The CDF is this function here. Okay, and this can be written as x less than x plus the probability that big X is equal to small x. If this guy is equal to 0, these 2 quantities are the same, and we don't have a jump. If this guy is strictly positive, like what happened at the values taken by a discrete random variable, then you will have a jump. Now, for singular random variables, the probability of singleton subsets of R is exactly equal to 0, so no jumps. So we don't have jumps here. Okay. It's weird distribution. I mean, singular random variables. You may think, okay, so this is like fiction, and we don't like in practice have things like this. But singular random variables in higher dimensions actually are useful. Excellent question. No PMF, no PDF. Okay, so PMF is for a discrete random variable, and it gives you the probability of singletons, the basically the values taken by the random variable. So this is discrete random variable. It has a PMF. I will talk about the usefulness right now. PDF, no, it does not. It does not have a PDF. Again, it's something. It's a theorem in measure theory that you cannot assign a PDF to this thing, and so you just have to do the CDF. So that's the power actually of the CDF. You can. The CDF is there for all types of random variables. PMF is something for discrete random variables. PDF is something for absolutely continuous random variables. The powerful thing that we will study in this course later that is also applicable to all types of random variables is called the characteristic function. This we can define for any type of random variables. But you know, the limitations of PDF and PMF are there. They are for specific types of random variables. Okay, CDF and characteristic functions, they don't have these limitations. You can apply them to any type of random variables. So for this guy here, for this monster, this no PMF, no PDF. Okay, we can just talk about its CDF. Okay, now in higher dimensions, singular random variables are basically more practical. So maybe something, you know, this counter random variable. Personally, I have never encountered it in any application. Okay, however, in 2 dimensions, what can be an example of a singular? What can be an example of a singular random variable? Okay, for example, in 2 dimensions, if you have like 2 dimensions x and x1 and x2, what about this is like I am getting ahead of myself because we haven't talked yet about random vectors. So random vectors are basically a collection of random variables. So it is basically the concept of random variables extended to multiple dimensions. So I'm getting ahead of myself. So no problem if you can just ignore this part, but I will say it anyways. So you can define the random variable on a circle. Okay, so you can define a random variable on a circle. So you can say that basically the PDF x1, x2 is basically 1. If this circle has a radius of a, it's 1 over 2 pi a, indicator that x1 squared plus x2 squared is equal to a squared. Okay, now here you are defining basically on a circle. Now a circle is a Borel set that has what is the cardinality of the points on a circle? C, right? So the number of points on a circle are basically like the number of points in an interval. It's the number of points on the basically the real line. Okay, so a circle is an uncountable set. And what is its Lebesgue measure? Now, since we are talking about 2 dimensions, now the Lebesgue measure is basically an area. And a circle in 2 dimensions, it has a Lebesgue measure equal to 0. Remember, we did like a proof, like maybe in the previous lecture, which like we proved that the Lebesgue measure of a line in 2 dimensions or higher dimensions will be equal to 0. You can basically repeat the same thing to a circle, apply to a circle. So basically, a random random variables defined as I did here, they are singular. They are singular because basically you apply them. You are defining, you are placing your probability on a Borel set, and this Borel set is uncountable and it has Lebesgue measure 0. Because a circle has Lebesgue measure 0 in 2 dimensions, and those you can think that something like it may appear in applications actually. Okay, so this is not like totally useless. So what I can say, if you don't have a flavor of multiple random variables or random vectors, you just have to wait. But singular random variables, they may appear to be totally like fictional, but they are they are useful if we talk about multiple random variables, and you can talk about like Gaussian random variables that are singular because their covariance matrix is has a determinant of 0. So I mean, it will come. Okay, so they are not, you know, singular random variables are not totally useless. Okay, and now if you see the definition of those three types of random variables, you will feel that, you know, they do not exhaust all possibilities, right? So discrete random variable takes finite or countably infinite values almost surely. Absolutely continuous, basically the probability of any Borel set of Lebesgue measure 0 is 0. Singular probability of the singleton subsets of big R is 0, but there exists some uncountable subset of R of Lebesgue measure 0 for which the probability is 1. But I mean, can we do more? So the answer is, surprisingly, you know, no. Those are the three pure types of random variables. In this lecture, we'll see an example. So you can have mixtures. Okay, so in total, we have 7 types of random variables: discrete, absolutely continuous, singular. So those are, you know, the pure guys. Okay, and then we can mix, so we can have discrete and continuous, discrete and singular, continuous and singular, or the 3 types together. Okay, so in total we have 7 types of random variables that are basically defined, and you cannot go outside. So there are like fundamental theorems tell you that this is what you can get. You cannot get, you know, more. If you want, like, if you want everything to be consistent, remember, you know, that there are probability measures. These are not arbitrary things. They have properties and so on and so forth. So things are constrained. So that these are the types that we get for random variables. So let's basically review the three quantities that, you know, will be useful to us in the remaining part of this course. CF, PMF. If you mix, you have a PMF for the discrete part and the BDF for the continuous part. You know, now there is an engineering trick. That allows you to, for example, talk about the PDF of a discrete random variable. Okay, so by using the Dirac deltas, we will not do this in this course. Okay, so again, if you want to be like very faithful to basically the foundations of probability as defined in math, then yeah, for example, there is no PDF for a discrete random variable. But you can, for example, talk about you will find, like, in engineering applications, sometimes we talk about the PDF of a continuous random variable, the PDF of a discrete random variable, and the PDF of a mixture of continuous and discrete random variables. So we had a PDF. And the idea here is actually that you use, you go to the Dirac deltas. The Dirac deltas will allow you to sort of define something like a PDF for discrete random variables. And so if you have like a mixture of discrete and continuous, you can actually talk about a PDF. But again, I will not assume that people here are very familiar with the Dirac delta and how it's employed. And so we will basically stick to the discrete PMF. That's it. Absolutely continuous PDF. And if you have a mixture, then the discrete part has its PMF, and the continuous part has its PDF. Okay. CDF is defined for everything, and so let's, as a review, remind ourselves of its properties. It is a function. By definition, it is defined as such. You have no option here. You cannot say that the CDF is x strictly less than small x. This is not how a CDF is defined. Okay, so these two guys can be equal to one another if the probability that big X is equal to small x is 0. However, generally speaking, this is not true. For example, if you have a discrete random variable that can take the value small x with a strictly positive probability. Okay, so you need to stick to the definition. The CDF is the probability that big X is less than or equal to small x. It's a function. Its limit as x goes to plus infinity is 1, x goes to minus infinity is 0. It is non-decreasing. It may remain flat, as we have seen for discrete random variables, and it may increase, but it never decreases. It may have discontinuities. That's not a problem, and we have seen this for discrete random variables. However, if it is discontinuous, if it has a jump somewhere, then it must be right continuous. It must be right. So basically, it satisfies this relationship. So if, which again, like maybe you prefer actually the graph. So the graph, if you have a jump, it will look something like this. And this is basically the definition of right continuity. Okay. If we talk about absolutely continuous or singular random variables, because the probability of singleton subsets of R, the probability that the random variable is exactly equal to some given real number is 0, then there will be no jumps. Okay, there will be no jumps, and so you will have a continuous function. Okay, but note that this is, for example, for absolutely continuous random variables, this is not applicable to the PDF. So the PDF may have jumps, but the CDF of a continuous or singular random variable will have no jump. It is a continuous function, and so basically, you will just see a curve that is changing smoothly. The probability of every singleton is equal to 0 for these two types of random variables, absolutely continuous and singular. Now, if you have a discrete random variable, or if your random variable is something with a discrete component, so it can be purely discrete, or it is discrete and continuous, or it is discrete and singular, or it is discrete and continuous and singular. If it has a discrete component, it means that there will be some alpha, okay, which is some given real number for which the probability that x is equal to alpha is strictly positive. In that case, you stare at the CDF and you will find a jump that looks like this. And this jump actually will be with the probability that x is equal to alpha. PMF is the business of discrete random variables. And it is simple, so basically the PMF is the probability that big X is equal to small x. And the sum of those probabilities, of course, should be equal to 1. And small x is part of a finite or countably infinite set. That's the definition of a discrete random variable. PDF is the business of absolutely continuous random variables. Okay. Again, this trick of assigning PDFs to discrete random variables via the Dirac deltas, we will not use basically this here. So PDF is for absolutely continuous random variables, non-negative. It's not a probability. You can use it to obtain probability. So if you want the probability from on some interval from A to B, just go and integrate this PDF from A to B. If you want to obtain the CDF from the PDF, integrate from minus infinity to basically to U. If you want the CDF evaluated at U, which is the probability that big X is less than or equal to U, then what you do is that you integrate from minus infinity to U. And from minus infinity to infinity, it should be 1. Okay, so it is a non-negative function, that basically integrates to 1. If you integrate it from minus infinity to some real number, it gives you the CDF at that real number. And if you integrate it from A to B, it gives you the probability that, of this interval, that basically, the probability you can write it in that X lives in A and B, this interval from A to B. Okay. So this is the PDF. It may be discontinuous. Now, can we do something opposite to this thing here? So if we can obtain the CDF by integrating the PDF, so it makes sense like to obtain the PDF from differentiating the CDF. Okay, so this is true, so long as basically the CDF is differentiable. Because we have seen an example which like the CDF is like for a uniform random variable, it is basically it's continuous. It must be continuous, but it has like 2 breakpoints at which the function is not classically differentiable. And so in that case, you apply this function, and it is valid so long as you are talking about the points of differentiability of the CDF. Okay, so let's take an example, and so this is CDF. Okay, and let's just think about it. Is this a CDF? Let's like sort of examine the properties. So limit as x goes to minus infinity is 0. So we are talking about 0 here, right? So we are going to 0. So it's 0 from here to minus infinity. Limit as small x goes to infinity is 1. So yeah, it goes to 1 and it remains there forever. Great. It is non-decreasing, so it may remain flat here, flat there, and here it is increasing, here it is strictly increasing. Great. And it is right continuous. So basically here you will find that it is right continuous. So basically at the point 1 over 3, the value of the function is the upper value here, which is 2/3. So this function that we see in front of our eyes is basically a valid CDF, and so there must be some random variable with this particular CDF. Okay, and from the CDF we can know things, things like what type of random variable are we talking about? So it's not absolutely continuous. It's not absolutely continuous because we have a jump, right? We have a jump at 1 over 3. And it's not discrete either because there is just one single jump, which is this jump here, and this jump is from 1 over 6 to 2 over 3. So in fact what we are seeing here is basically a mixture. So this is a mixed random variable that is discrete and absolutely continuous. Okay, so let's actually go and compute some probabilities and see how the CDF can be used to basically obtain probabilities. What is the probability that x is equal to 1 over 2? So where is 1 over 2? 1 over 2 is living somewhere here. So this is 1 over 2. And, at 1 over 2, the curve for the CDF is continuous, right? No jumps or anything. And this is an indication that the probability that x is exactly equal to 1 over 2 is equal to 0. You don't see a jump at 1 over 2. And this probability is equal to, so probability that x is equal to 1 over 2 is the probability that x is less than or equal to 1/2 minus the probability that x is strictly less than 1 over 2. And again, there is no jump here. The function is continuous at this point 1 over 2, not just continuous. And so basically these two quantities are the same, and the probability of x being exactly equal to 1 over 2 is 0. At 1 over 3, the story is different because we have a jump, and the value of this jump is actually the probability that x is 1/3, and the jump here it's from 1/6 to 2/3, and so the difference is 1/2. So this is the probability that x is exactly equal to 1 over 3. Okay. Now, what is the probability that x is less than or equal to 1 over 4? Okay, so what is this thing? This is by definition. So by definition, this is how the CDF is. This is the CDF evaluated at 1 over 4, right? By definition, the CDF gives you this piece of information. The probability that big X is less than or equal to some given number. So you can just read it from the graph. So you go here. So 1/4 is, let's say it's some point here, 1/4, and so you go. You hit the CDF curve and say, okay, what is this value here? Okay, or you can just substitute in the function, and you will find that this function is a line with a slope 1/2, and so the probability that x is less than or equal to 1 over 4 is 1/2 times 1 over 4, which gives you 1 over 8. So what is the probability that x is strictly less than 1 over 4? Now this is not the definition of the CDF. Okay, but it is basically the CDF evaluated at 1/4 minus basically the probability that x is exactly equal to 1 over 4. Same story as we did at the beginning, at 1/2. At 1 over 4, the CDF curve is continuous. Continuous means that the probability of big X taking this exact value 1 over 4 is 0. And so the probability that X is less than 1 over 4 is also 1 over 8. Again, because at 1 over 4, the CDF is continuous, then these two guys are equal. Probability that X is less than or equal to 1/3, again, by definition, this is the CDF. This is Fx of 1/3, and you go and read it directly from the curve. So the curve is 2/3. Okay, so this is 2/3. But if you say that it is strictly less than 1/3, then this is not the definition of the CDF, but it is the CDF, which is 2/3 minus the probability that X is equal to 1 over 3. Now, the probability that X is equal to 1 over 3, now it is not 0, because actually at 1 over 3, there is a jump. And basically, the jump value will give you the probability that X is equal to 1/3. What is the probability that X is living between 1 over 3 and 1? So you can write this probability. So we want the probability that X is greater than or equal to 1/3, less than or equal to 1. Well, this is the probability that X is less than or equal to 1. Okay, minus the probability that X is less than 1/3. Okay, and the way of seeing it, that basically you are saying that the interval from 0 to 1, you can think of it as like the union of two intervals, right? So one interval, let's say from 0 to 1/3, union the interval from 1/3 to 1. Okay, and so the probability of 0, 1, and our random variable, the probability that it is less than or equal to 1 is 1, so it is living there between 0 and 1. So the probability of 0, 1. So if you want to do this in slow motion, probability 0, 1 is 1. And because these two guys are disjoint, we have additivity. So basically the probability of the union is the sum. So this is the probability, of X being strictly less than 1/3, plus the probability that X is between 1/3 to 1 inclusive. And so this probability here we are interested in will be 1 minus this probability. So it's 1 minus this probability. And what is the probability that X is strictly less than 1/3? We computed it as 1/6. So this is what we get here. Okay, so you can use the CDF to compute probabilities as such. And our random variable, as I said, is not discrete. Because if it's discrete, then basically it just has one jump. And if it's discrete, then at this jump, the probability should be equal to 1. So it should jump from 0 to 1 if it's just one jump. But we have just one jump, and the jump is with basically is of value 2/3 minus 1/6. Okay, and so it is not equal to 1. So we have actually a mixture between a discrete and continuous random variable. So the way of thinking about it is the following. You can think of our random variable X. Okay. So it is equal to 1/3. Okay, so it is 1/3. What is this 1/3? The value at which the CDF makes a jump. And it's the only value in this particular example. Okay, so X is equal to 1/3. And what is the probability? So this is basically the value of the jump. Okay, and then I'm claiming that basically this 1/3, it has a probability 1/2. Then the other half, because probabilities should be give you 1. So this X is 1/3 with probability 1/2, and with probability 1/2, it is uniform 0, 1. How did I know this? How did I know that basically that X is it has the continuous part is a uniform part? Because the total probability is 1, but I want to say why uniform? How did I know that it's uniform, not nothing else? Linear function, exactly, linear function. So the CDF. So in other words, if you think about the derivative, right? So if you take this CDF and you try to differentiate it, if you take the CDF and you try to differentiate it, where the function, the CDF itself is differentiable. So you will find that. So let's put this here. So the derivative of f of x, if you draw it, so the derivative is 0, right? And then here the derivative is like 1/2. Okay, so till we reach 1/3. Okay, so basically this is 1/2. This is the slope. Okay, so this is the slope here. And then if you differentiate this guy, what is the slope? Here is the function. It's also 1/2 up to 1. Up to 1, and then it goes to 0 because this part is flat. So if you differentiate it, what do you get? You get a flat curve. You get, a flat curve, and this flat curve is basically, if this flat curve has a height of 1, then this will be a uniform 0, 1, right? If this flat curve is basically 1, then we are actually talking about the uniform probability measure from 0 to 1. In our case, it's half because the random variable is not fully the uniform 0, 1 random variable. It has a discrete part. Okay, so here the idea is the following. It's as if our random variable, it has again two components. So there is a discrete component which has a probability of 1/2, and then you take the probability of 1/2 and you assign it to the continuous component, which is here is the uniform. Okay, so when you differentiate the curve, you don't expect to get 1. You get 1 if actually we are talking about a pure, absolutely continuous random variable. But you get half. Again, so if you integrate this thing, what is the area under the curve? Area is equal to 1/2 because x is not uniform 0, 1, right? X is 1/3 with probability 1/2 and uniform 0, 1 with probability 1/2. So you can think of it like this. Now, sometimes just work with the CDF and you do not even need to bother about how to interpret the type of random variable. So in many cases, I give you the CDF and you are asked to compute probabilities. Our first discussion here, you don't even need to think about what type of random variable there is. Okay, it's like sort of an extra question, and sometimes actually it is not even useful. Okay, unless of course you are asked what type of random variable is this. Okay, the CDF has enough information to compute every probability that is relevant in any practical application. You may take it a step further and say, okay, so what is the type of this random variable? Definitely it's not discrete because there is a jump, but this jump, it's a single jump. For discrete random variables that take only one value with probability 1, you should have just one jump with a value of 1. But here our jump is with a value of basically 1/2. So it's not totally discrete. It's not totally continuous because we have a jump. We have a discontinuity in the CDF. So it is a mixture, and we can think of it again as if we have like this random variable that is 1/3 with probability 1/2, and with probability 1/2 we are talking about a uniform from 0 to 1. And I knew that it is uniform by simply differentiating and discovering that the PDF will be a constant. The PDF will be a constant line. The curve that we get after differentiation, it will not integrate to 1. It will not integrate to 1 because there is a discrete component. But what should always be true is that the integral of this, the area here, plus the value of the jump, this is 1. Okay. Where is the protein? So the 1/2, I mean, basically this 1/2, it comes, I mean, there are so many 1/2s here, but this 1/2, when I differentiate, it's because we are differentiating. So this is the slope here and there. So if you just differentiate, you will find that you get a flat line with probability 1/2, and the area under the curve will be 1/2, not 1. And the reason is that the probability, this random variable is not uniform 0, 1. It is uniform 0, 1 with probability 1/2, which is the total area under the curve, and then with probability 1/2, which is equal to this jump here. It is equal to exactly this value, which is 1/3. Okay. So we will not, we will keep talking about, PDF, CDF, PMF, and use them. So of course, I mean, this is basically we are like putting the parts of the puzzle. So it's not it's not the end of the story. I mean, we will talk about these, and we'll talk about like important uses in application, which like you don't just deal with a random variable, you deal also with functions of random variables. Okay, so this will come, but before doing that, we need to talk about things that are defined for random variables that are very important and very useful in practice. They are called the moments of the random variable. And our focus now will be the first moment of a random variable, also called the expectation or the mean value. Now, to define a moment for a random variable, okay, let's start first by assuming that our random variable is non-negative. So it means that x is greater than or equal to 0. Okay. Now, if we have a non-negative random variable, we can define this so-called first moment or mean, and it is basically what you may think of as the average value. It's defined as such. We will give like 2 definitions depending on whether our random variable is, and let's for now ignore mixed random variables. Let's assume that and let's ignore singular random variables. Okay, so we will focus that big X is either a discrete random variable with a PMF or a continuous random variable with a PDF. If our random variable is discrete, then basically its first moment is given by this summation here. Okay, so if the random variable takes the values, so X is in a small x1, x2 with probability 1. If this is our discrete random variable, then its first moment, written with this E like this, and X is basically a summation, K from 1 to infinity, of those values, each one weighted by its probability. Okay, so xk, the values taken by the random variable, multiplied by the probability. Okay, so definition. So this is not like, this is how we define the first moment or the expectation. So if the random variable is discrete and it takes values, we take each value, we weight the value by its probability, and then we do a summation. So when you do this, you get a number. Okay, you get a number. Or you may get infinity, right? Because you are summing. Now, if the random variable takes finite values, this is guaranteed to be a finite sum. But there are, if it's an infinite sum, there is a possibility that this thing is plus infinity. If I want to write this in terms of the PMF, this is the PMF. So I can write this as k from 1 to infinity, xk. This is the PMF of x because it is assumed to be a discrete random variable, xk. This again is just, by definition, this is equal to that. What are the possibilities of this expectation? Now, once you compute it, again, we are assuming that those guys are non-negative initially, and so x is greater than or equal to 0. basically expectation of x. It will be a non-negative number, but it can be plus infinity, like this. In the previous course on probability, you may say that if this is not finite, you may say that the first moment does not exist. Now, in advanced probability, this is not useful. We will say that the first moment is plus infinity. So there will be cases in which the first moment is not defined, and I will come to them perhaps in this lecture or in the next lecture. But in this course, again, let's start basically differentiating between the case of infinity and not defined. So we may get a finite result, and we may get an infinite result. This is legitimate, and sometimes it's very useful. Okay, so keep this in mind. For non-negative random variables, the first moment always exists as a finite non-negative real number or as plus infinity. Okay, if we allow our random variable to be general, that can take positive and negative values, then in this case there will be a situation in which the first moment of the random variable is not defined. It does not exist. Okay, so does not exist for us here, it will mean it's not defined because there is some mathematical problem, as we will see. But having the sum that is plus infinity for us will be something that is okay. For continuous random variables, we will basically mimic this thing. So this is if x is discrete, x continuous. Okay, again, the formal name is absolutely continuous, but I will just say continuous. The expected value will be defined in terms of the PDF, and it will be from 0 to infinity, because remember the random variable is non-negative. You take small x, you weight it by what? So here we are weighting by the PMF, here we will weight by the PDF. Okay, and again, this will be something that lives between 0 and plus infinity included. Okay, so this is by definition the first moment or the expectation or the mean, okay, of a non-negative random variable if it is discrete and if it is continuous. If it is discrete and if it is continuous. Okay, and later I think through an exercise we will learn how to express. It is very important to know how to express the expectation in terms of the CDF. Because if you express the expectation in terms of the CDF, you will be, you can now play with all types of random variables, because every type of random variable has a CDF. Okay, but for now, let's just stick to random variables that are purely discrete, and this is their first moment in terms of the PMF, or purely absolutely continuous, and this is the first moment in terms of the PDF. Okay. Can this guy be 0? Yes, it can be 0, and after studying something called the Markov inequality, we will talk about this specific point. If you have a non-negative random variable, what does it mean? What does it mean that its first moment is exactly equal to 0? Let's take an example. So suppose that your random variable has this PMF. So this is the PMF. And basically, this random variable is defined, okay, so it's defined for x, it's a natural number, 1, 2, 3, and so on, so it's non-negative. And the probability that big X is equal to small x, one of those guys here, is 1 over x cubed. So we divide, so what is the probability that big X is equal to 3? So it is 1 over 3 cubed, okay. But remember that basically the probabilities should all sum to 1. So you need like a scaling factor so that everything sum to 1. And so we will divide by zeta of 3. Okay, so just a reminder, what is the zeta function? So the zeta function is basically this summation. n from 1 to infinity, 1 over n to the power s. So if I write it like explicitly, this is 1 over 1 to the s, plus 1 over 2 to the s, plus 1 over 3 to the s, plus 1 over 4 to the s, all the way. So basically, this PMF, it needs this scaling factor. Let's see why. Because if I tell you that the probability is 1 over is something, so that the probability that big X is equal to 1 is some constant times 1 over x cubed. How do you determine the constant? You need the sum over x1, 2, 3, and so on. This summation should be equal to 1. And so it must be the case that C multiplied by this summation should be equal to 1. And this summation by definition is the zeta function evaluated at 3, because those guys are cubed. And so this is zeta, C zeta 3 multiplied, C multiplied by zeta 3 equal 1. And so C, to have a PMF that is correct, okay, so the sum of the probabilities should be 1, it must be the case that this constant C is chosen as 1 over zeta 3. Okay, so that's, you know, the reason that we have this guy here. Now, what is the first moment? So the first moment, again, by definition, what do you do? For discrete random variables, you have a summation over the values taken by the random variable with probability 1, or almost surely. And so those values are basically the small x's, are the natural numbers. You weight each value by its probability, which in our case here will be 1 over x cubed multiplied by this, you know, normalizing factor 1 over zeta of 3. So basically, what is this summation? X multiplied by 1 over x cubed, this will be 1 over x squared. And if the power now becomes 2, then we are talking about zeta of 2. And zeta of 2 is a famous number, which is pi squared over 6. Okay. And zeta 2 is a finite number over zeta 3, and so you get something that is finite. Zeta 3 is also finite. We are sure that you know, the sum is finite and the ratio will be a finite number. So this is a discrete random variable with a finite, strictly positive first moment, or mean, or expectation. Now, what if we define a discrete random variable such that the probability now is 1 over x squared? So again, you can play the same game and say, if I want the probability to be proportional to 1 over x squared, what should be the factor of proportionality? So you do something like here, but it is 1 over x squared, so you will discover that now your normalizing constant should be 1 over zeta 2. So what will be the first moment? The first moment will be, you know, again, you take x. Let me write it like this. You take x, you multiply it by its probability, which is 1 over zeta 2, 1 over x squared. This is a constant. You can pull it outside, and then you can basically sum. But when you multiply x by 1 over x squared, you get the summation 1 over x, which is zeta 1. And zeta 1, this is the harmonic series. And so you get infinity. So you get infinity over a finite number, and so you get infinity. So this is an example of a discrete random variable whose first moment is plus infinity. Now, for the continuous case, you know, there are famous random variables called the exponential ones, and this is their PDF. Okay, so how do we compute the first moment? So the first moment, again, the rule is our random variable is non-negative, so we have an integral 0 to infinity. Then you have a small x, and you weight it by the PDF, depending on the PDF. So exponential, you go and look it up. Basically, the PDF, it looks like this: some positive parameter lambda e to the minus lambda x dx, and then you do this integration, you know, and you find that it is equal to 1 over lambda, and so it is 1 over a strictly positive number, and you get something that is finite. You can define another, so this is another PDF, okay, which is given here. You can basically verify that it is a PDF. Okay, how do we verify that something is a PDF? It should be non-negative. So if I give you a function and ask you, how do we even know that this is a valid PDF? So it should be non-negative. At no point it can be negative. It should be non-negative. Okay. What else? What else? It should be basically its integral from minus infinity to infinity should 1 exactly. And so you can basically take this thing, and if you integrate it from 0 to infinity, 1 over 1 plus x squared dx. So this is 2 over pi, tan inverse x, and then you take the limit as x goes to infinity. Tan inverse infinity is pi over 2, and tan inverse 0 is 0. So that's pi over 2 times 2 over pi, that's 1. Okay, so this is a correct PDF. Now, as a technicality, I said something, it's not totally like accurate mathematically. Okay, so actually a PDF, you can make the PDF negative. Okay, so I will say something annoying. I mean, you can just ignore what I am about to say, but you can make the PDF negative on a set of measure 0, on a set of Lebesgue measure 0, and it's fine, and it is fine, because typically the PDF has no meaning as a probability, and we obtain probabilities from PDFs via integration. And integration basically does not care about so if you have a function, a PDF that is negative, actually it can be even minus infinity at a set of Lebesgue measure 0 at a point or several points, then its integral will be exactly the same as you remove those negative parts. So I mean, it's not negative. So basically the correct way of saying it is that the PDF should be non-negative almost everywhere. So that's the technical term for the purpose of this course. And if it feels confusing, you can just take it that the PDF is non-negative everywhere. Okay, but I mean, strictly speaking, it is non-negative almost everywhere. And there is like a technical difference between these two guys. Anyways, what if you compute the expected value of x? So it is apply the definition. So you take basically integral from 0 to infinity. Integral from 0 to infinity is just because our guys for now are non-negative random variables, so their values are from 0 to infinity. You take small x, and then you multiply by the PDF, copy and paste, 2 over pi, 1 over 1 plus x squared dx, and then you try to do the integration. And if you do the integration, you will find now that you get basically the natural logarithm. And when you put the upper limit of integration, take the limit, the logarithm of something that is arbitrarily large is infinity. And so this guy is plus infinity. Okay. So the moral of the story is, for non-negative random variables, the first moment always exists as a finite real number, a finite real non-negative number, or as plus infinity. And you can come up with examples for discrete and for continuous random variables for which the first moment is either finite or is equal to plus infinity. Okay? So the next step will be to basically define the first moment for random variables that can be positive or negative. Something like Gaussian, for example, it can be positive, it can be negative. So there are so many practically useful random variables in which like you cannot just stick to this non-negative thing. Sometimes you have to basically have your random variable taking negative values. And so how can we define the first moment for those guys? Okay, so the trick is, for example, you may say, well, if our random variable is absolutely continuous, for example, rather than having our integral from 0 to infinity, let's just have it from minus infinity to infinity, because we are allowing small x to be negative, but this is not always valid. Okay, and so the correct way of doing it, again, says this is related to how basically measure theory works and Lebesgue integrals. what we think of is that we take our random variable and think of it as two random variables. So we think of our random variable as basically composed to something called x plus and x minus.